The subject of this lecture is the various measurement systems that are in common use in today's science and technology. I will introduce the units used in specifically the metric system, unit conversions, and we're going to talk about area and volume. Historically, there have been many measurement systems used in different regions of the world, but over time, two systems of measurements have emerged and solidified as the main measurement systems used today. The imperial system is in use in the United States and several other countries in the world. And this system is based on units that come from the British Empire historically. Examples of units in the imperial system are feet, inches, pounds, PSI, FPS, mph, miles per hour, Fahrenheit, and so on and so forth. The other measurement system in common use today is the metric system. This system is used in most of the world. Some units that are commonly used in this system are the meter, centimeter, the Newton, that's the unit for force. Pascal is the unit for pressure. Meters per second, units for speed or velocity. Kilometers per hour, also units for speed or velocity. And for temperature, we have the Celsius or the Kelvin. So in this course, we are going to use predominantly the metric system in describing the various physical phenomena and also solving problems related to those phenomena. But we are also going to have some problems that will be done using the imperial system. Through the rest of the lecture, I'm going to focus on the metric system. So I'm going to introduce the unit, some common units or units that are mostly used through this course from the metric system, various relationships between different scales of the same unit for measuring large or small quantities of the same quantity. And I'm going to talk about conversion of units, and I'm going to discuss the base 10 origin of the metric system and how that is used to scale units up or down. So the metric system has two types of units of measure. We have basic units and we have derived units. So first, let's discuss the basic units of the metric system. In the metric system, there are certain quantities that are considered fundamental in nature and in their role of describing various phenomena. And so those quantities were assigned units of measure known as basic units. Those basic units are defined by standards of measure. For example, length is a fundamental quantity, and its unit of measure is the meter, and the basic unit is 1 meter. So 1 meter is defined as the distance that light travels in vacuum in 1/299,792,458 of a second. Since the speed of light is a fundamental quantity that is determined with extremely high accuracy, the standard for length, again, what 1 meter is as far as length is concerned, is defined extremely accurately. And so similarly, the other basic units in the metric system are defined with their own standards based on different fundamental constants in nature. There are 6 basic units. There are 7 basic units in the metric system. And this table here shows those basic units and what quantities are they assigned to. So first we have the meter, which has an abbreviation of with M, and this is the unit for length. Then we have the kilogram, which is abbreviated with kg, and that is the unit for mass. We have the second, which is abbreviated with an S, that is the unit for time. We have the ampere, which is abbreviated with A, and that is the unit for electric current. We have the Kelvin, abbreviated with a K, that is the unit for temperature. Candela, abbreviated with CD, is the unit for light intensity. And then we have the mole, abbreviated with MOL, which is the unit for molecular substance. So all of these units are defined through standards which use fundamental constants, and therefore they are never changing as far as the definition of each base unit and how we measure it. And so we can now build all the other units in the metric system based on various combinations of those basic units. In the metric system, all units that are not fundamental units are referred to as derived units, and they are assigned to quantities that are not considered fundamental quantities. Here is a small list of some units in the metric system which are assigned to quantities that are not fundamental, so those are derived units. For example, the liter, which is abbreviated with L, is a unit for the volume of a fluid, so that would be a liquid or a gas. The cubic meter is also a unit for volume, abbreviated with meters to the 3rd power. That unit is used typically for the volume of solids. The square meter, abbreviated with meters to the 2nd power, is the unit for area. The Newton, abbreviated with capital N, is the unit for force in the metric system. Meter per second, abbreviated with M/S, is the unit for speed. The joule, abbreviated with J, is the unit for energy. And the watt, abbreviated with W, is the unit for power. So these derived units are made of some combination of basic units. As you can see here, for example, the unit for speed, meters per second, is the combination of the unit for length, meters, divided by the unit for time, seconds. As we will see later, the Newton, which is the unit for force, is equal to the product of the units for mass, the kilogram, the units for length, meters, divided by the unit for time to the 2nd power, and that is the second squared. The joule, which is the unit for energy, is made from the product of the unit for mass, the kilogram, and the unit for length to the 2nd power, so meters squared, divided by the unit for time to the 2nd power, or seconds squared. So you see how these derived units are made from some sort of combination of basic units. The metric system is a base 10 system. What does that mean? It means that all denominations of a measurement unit can be derived from the basic unit by simply multiplying with some power of 10. An example of a base 10 system that is not related to measurement but operates on the same principle of moving between various denominations is the money system. The base unit for money in the USA would be the dollar. And then if we multiply by 10, we get $10. If we multiply by 100, that is $100. Then we have $1,000, 10,000, so on and so forth. And then we can go the other way, where dividing by 10 gives us $0.1, dividing by 100, $0.01, and so on and so forth. So moving between the different denominations in that system, the money system, is done by by multiplying with powers of 10. So similarly, in the metric system, the movement between various denominations of the same unit is done by multiplying with different powers of 10. So let's give an example of that. So let's look at the basic unit for length, and that is the meter. So if I take 1 meter and multiply it by 1,000, that is the same as multiplying this 1 meter by 10 to the third power, because 1,000 is equal to 10 to the third power. And so then this multiplication gives me 10 to the third power meters, which is also known as 1 kilometer. And we are going to talk about the naming of these denominations in a bit. Now, if I take 1 meter and multiply it by 1 over 100, that is the same as multiplying this 1 meter by 10 to the negative second power, which gives me 10 to the negative 2 meters, or also that is 0.01 meters. And this is called 1 centimeter. Finally, I can also take my 1 meter and multiply it by 1 over 1,000. That is the same as multiplying the 1 meter by 10 to the negative 3. And that is equal to 10 to the negative 3 meters, or 0.001 meters. And this also has a name, and that is the millimeter. So that is 1 millimeter. So here I moved between several different denominations of units for length, starting from the basic unit, which is the meter. I went larger than a meter by 1,000 times, so that is the kilometer. I went smaller than the meter by 100 times, that is the centimeter, and smaller than the meter by 1,000 times, and this is the millimeter. So similarly, I can move between various denominations for the other measurement units in the metric system, no matter if they are basic units or derived units, by simply multiplying by a power of 10. Let's talk about the denomination representation of units in the metric system. The denominations of any unit can be presented as a power of 10 notation or in a prefix notation. So let's discuss those two types of notations. So in power of 10 notation, the three denominations of units for length are presented. 1,000 meters is presented as 10 to the third power meters. 0.01 meters is presented as 10 to the negative second power meters. And 0.001 meters is presented as 10 to the negative third power meters. And in prefix notation, 1,000 meters is 1 kilometer. 0.01 meters is 1 centimeter, and 0.001 meters is 1 millimeter. So here the rule for naming is that the last symbol or letter in the unit is the basic unit, and what is in front is the prefix. So we have K as a prefix in front of meters, so we have that prefix is called kilo. C is a prefix here, and that is called centi. M is a prefix here, and that is called milli. So to keep up with all these various prefixes and powers of 10 that correspond to them, here is a table of the prefixes in the metric system. So we have the kilo, which we discussed on the previous slide, abbreviated with a K, and to that we have 10 to the third power correspondence. And here it is, kilometer, that is equal to 10 to the third meters. We have the centi, which is 10 to the negative second power. That's the centimeter, or in other words, 0.01 meters. We have the milli, that corresponds to 10 to the negative third power, and the millimeter is equal to 0.001 meters. We have also the micro, which is abbreviated with the Greek letter mu, and so 10 to the negative sixth power corresponds to that prefix, and so the micrometer is 10 to the negative 6 meters. And then we have smaller denominations, the nanometer, the picometer, the femtometer, and of course we have larger denominations, the gigameter, the megameter, the gigameter, and so on and so forth. So the same nomenclature of prefixes and power of 10 correspondence can be applied to other units, to all other units in the metric system. It can be applied to kilograms, to newtons, and so on and so forth. Scientists and technicians often use very large or very small numbers. For example, the thickness of an oil film on water is about 0.000001 meters. Or the distance between the Earth and the Sun is astronomical. And so how do we deal with such large numbers in a way that is easier to manipulate? How do we represent them? Well, there is a way that people have come up with, and that is called scientific notation. So by definition, a number is presented in scientific notation by moving the decimal point behind the first non-zero digit and multiplying by a power of 10. The exponent of the power of 10 is equal to the number of spots that the decimal point was moved, and then the sign of the exponent is positive when the decimal point was moved to the left, and negative when the decimal point was moved to the right. So let's look at several examples. 0.0000001 can be presented in scientific notation as 1 times 10 to the negative 7th power. So how did I get there? So I took my decimal point and I moved it 1, 2, 3, 4, 5, 6, 7 spots, so that according to the definition, the decimal point is behind the first non-zero digit, so this is 1 in this case. And then I multiplied by power of 10. So the exponent of the power of 10 is equal to the number of spots that I moved the decimal point by. So that is 1, 2, 3, 4, 5, 6, 7 spots, so 7. And then the sign in front of the exponent is determined by the direction in which the decimal point was moved. Since I moved the decimal point to the right, that means that I must put a minus sign in front of the exponent. And so again, 0.0000001 is equal to 1 times 10 to the negative 7th power. Similarly, I can write 10,000 as 1 times 10 to the 4th power. So in this particular example, the decimal point is not shown, but we know that the decimal point is behind the 0 right here. And so if I take the decimal point and move it 1, 2, 3, 4 spots to the left so that it gets behind the first non-zero digit, which is the 1, that means that the result would be 1 times 10 to the 4th power, where 4 is equal to the number of spots that I moved the decimal. And since I moved the decimal point to the left, the power the sign in front of the exponent here is a positive sign. Now let's look at this next example, presenting 0.058 into scientific notation. So I'm going to take my decimal point and move it 1 2 spots so that I get it behind the first non-zero digit, which is 5. And so then I can write the left-hand side in scientific notation as 5.8 times 10 to the negative second power. And finally, I want to write 73,845,001 in scientific notation, so that would become 7.3845,001 times 10 to the 7th power. Again, the decimal point is not shown here, but we know that it's behind the 1. And so I move it 1, 2, 3, 4, 5, 6, 7 spots to the left, so that it places behind the first non-zero digit, which is 7. And then I end up with 7.3845,001 multiplied by a power of 10, and so this power of 10 has an exponent equal to 7, equal to the number of spots I moved the decimal point. And since I moved the decimal point to the left, then the sign in front of the exponent is a positive. And so any large or small number can be presented in scientific notation by just using this definition here. And of course, following the convention for the sign of the exponent based on in which direction do we move the decimal point. Calculating results, where the calculation requires operations with quantities presented in scientific notation, meaning in power of 10 notation, requires knowledge of operations with powers of 10. So let's look at how do we multiply powers of 10 and how do we divide powers of 10. So when multiplying 2 powers of 10, we would simply add the two exponents. So for example, if I have 10 to the power a multiplied by 10 to the power of b, that is simply equal to 10 to the power of a plus b. And here a and b can be both positive, both negative, or a positive and negative number, or even fractions, it doesn't matter. And so here is an example. I want to multiply 10 to the second power by 10 to the third power. By my definition here, that is equal to 10 to the power of 2 plus 3, which is 5, so that is equal to 10 to the fifth power. Here is another example. I want to multiply 10 to the negative third power by 10 to the negative fourth power. So according to my rule, that would be 10 to the negative third power plus minus 4, or that is 10 to the negative seventh power. And finally, I want to multiply 10 to the negative second power by 10 to the fourth power. That would be equal to simply 10 to minus 2 plus 4, or that is 10 to the second power. Now for dividing powers of 10, we take the two powers, we take the two exponents and we subtract them from each other. So for example, if I have 10 to the power of a and divided by 10 to the power of b, that is simply equal to 10 to the power of a minus b. So here you have to be careful with the sign of b, because if that's a negative power, the two minuses will produce a plus here. So let's look at several examples. So first I want to divide 10 to the second power by 10 to the third power. According to my definition here, that is equal to 10 to the power of 2 minus 3, which is the same as 10 to the negative first power. Now I want to divide 10 to the negative third power by 10 to the fourth power. So this is equal to 10 to the minus 3 minus 4, or that is 10 to the negative seventh power. Finally, I want to divide 10 to the negative 3 by 10 to the negative 5, or 10 to the negative fifth power. So this would be 10 to the negative 3 minus 5. And so that is 10 to minus 3 plus 5. Finally, this is 10 to the second power. So here it's important to be careful about the signs. We have negative fifth power, but we have a minus in front here, so that's going to produce a plus. And then we have 5 minus 3 essentially, and that is 2, so 10 to the second power. In the next several slides, I will discuss the idea of conversion of units and I will start with one of the fundamental quantities in the metric system and use that as an example, and that quantity is length. So for length, the basic unit or the unit in the metric system used for length is the meter, abbreviated with m. And the base unit for length is simply 1 meter. So anything larger than 1 meter or smaller than 1 meter is no longer the base unit. And again, the denominations for length we achieve by multiplying or dividing by powers of 10. When there is a need to measure shorter or smaller lengths, typical units that are used are the centimeter and the millimeter. So 1 centimeter is equal to 10 to the negative 2 meters, or 0.01 meters. Or we can reverse this and say that 100 centimeters are equal to 1 meter in length. And then 1 millimeter is 10 to the negative 3 meters, or 1 millimeter is equal to 0.001 meters, or 1,000 millimeters is equal to 1 meter. So all of these are equivalent, meaning these representations here between the relationship of a centimeter and a meter are all equivalent, and these representations for between the millimeter and the meter are all equivalent, just written in a different way. And for large distances, the typical unit that's used to measure those is the kilometer. 1 kilometer is equal to 1,000 meters, or 1 kilometer is equal to 10 to the third power meters, or if we reverse that, 0.001 kilometer is equal to 1 meter. So again, these relationships are all identical as far as the relation between a kilometer and a meter is concerned. They are just written in a different way. Well, sometimes it is necessary to do a conversion between denominations of the same unit for the purposes of solving a problem. So for example, let's say we have the length of something measured in centimeters, but for the purposes of calculation, we need that length in meters or in millimeters. So we must do a conversion between those two units. So the conversion between denominations of the same unit is done by using a conversion factor. The definition of conversion factor is very simple. A conversion factor is an expression used to change from one unit or set of units to another. The basis of creating a conversion factor lies in the fact that multiplication by 1 does not change the result, and also in the fact that the ratio of the same quantity measured in two different units is equal to 1. So for example, from the previous slide, we know that 100 centimeters are equal to 1 meter. So if I make the ratio of 100 centimeters divided by 1 meter, since those two measure the same length, then that ratio is equal to 1. This is just the ratio of two different units used to measure the same length. And so I can also flip this ratio and have 1 meter divided by 100 centimeters. Again, those two measure the same length, so therefore the ratio is 1. And so these two ratios are called conversion factors for the conversion between centimeters and meters. I can use the same idea to create conversion factors between millimeters and meters. We know that 1,000 millimeters is equal to 1 meter, so therefore if I create the ratio 1,000 millimeters divided by 1 meter, that will be equal to 1. And I can also flip the ratio to get 1 meter divided by 1,000 millimeters, that's also equal to 1. So those two conversion factors convert between millimeters and meters. Similarly, I can create a conversion factor for converting meters to kilometers or kilometers into meters. I can create a conversion factor that converts derived units such as meters per second into kilometers per hour, and so on and so forth, as long as I know the relationship between the individual units that are used to make the derived unit. So how exactly does one choose a conversion factor when they want to do a conversion of units? So first we must define units as in old units and new units. So old units are the units that we want to convert from. Let's say the original units of the quantity were whatever, meters or kilometers or meters per second or kilometers per hour or something else. And we want to change those units to some other units, which we will call the new units. And so those will be the units that we want to convert into. So again, old units are the units we want to convert from, and new units are the units we want to convert into. So here are the basic or simple rules of how to create and use the conversion factor when we're converting between old and new units. If the old units are in the numerator in the original expression, then the old units must be in the denominator of the conversion factor, and the new units in the numerator of the conversion factor. The second rule states that if the old units are in the denominator in the original expression, then the old units must be in the numerator of the conversion factor, and the new units in the denominator of the conversion factor. So let's show several examples of conversions to illustrate how the conversion factors are selected. So first, let's convert 120 centimeters to meters. So the old unit here is the centimeters. Those are the units of the original expression. And the new units will be meters. Then we also notice that in the original expression, the old units are in the numerator, which, following the rules of creating conversion factors, means that the old unit must be in the denominator of the conversion factor. So I know that the relationship between meters and centimeters is given by this relationship here. 1 meter is equal to 100 centimeters. So since I want my old unit to be in the denominator in the conversion factor, I take the ratio between 1 meter and 100 centimeters as such, 1 meter divided by 100 centimeters. So the old units, centimeters, is in the denominator of this conversion factor. And now let's remember also that this conversion factor is equal to 1, since both units, meters and centimeters here, measure the same length. 1 meter is equal to 100 centimeters. Okay, so now I will multiply the original quantity, 120 centimeters, by this conversion factor. So 120 centimeters times 1 meter divided by 100 centimeters. This can be rewritten as 120 centimeters times 1 meter, and the entire thing divided by 100 centimeters. The units of centimeters cancel out because we have them in the numerator and denominator. And so what we are left with is 120 divided by 100, and the new units are meters. That's what's left from the units after the cancellation here and here. And so 120 divided by 100 is equal to 1.2, and the new units would be meters. So 120 centimeters is equal to 1.2 meters. So as we saw here, when we have the same unit in the numerator and denominator, we can cancel them out. Let's do another example. Let's convert 19 inches to centimeters. Well, in order to do that, we must know the relationship between inches and centimeters, and this relationship is that 1 inch is equal to 2.54 centimeters. So I'm going to use this relationship to create a conversion factor. So since I'm converting from inches to centimeters, inches are the old units and centimeters are the new units. So therefore, since inches are in the numerator here in the original expression, that means that in the conversion factor, inches must be in the denominator. So the conversion factor then would look like so: 2.54 centimeters divided by 1 inch. So I will multiply 19 inches by 2.54 centimeters divided by 1 inch. That I can rewrite as 19 inches times 2.54 centimeters, the entire thing divided by 1 inch. The units of inch are in the numerator here and the denominator here. I can cancel them out. And so what I'm left with is 19 times 2.54 divided by 1, and what's left is the new units, centimeters. And now let's calculate the final result, and that is 48.26 centimeters. Now let's look at a quantity, physical quantity, which unit is derived from the unit of length. And so this physical quantity is the area. Area is defined, the area of a figure is defined as the number of square units that it contains. Typical units of area are square inches, square feet, square centimeters, square meters, or meters squared. Then the question is, how do we calculate the area of a figure? So for simplicity, we are going to consider only nice shapes, such as rectangles and circles. However, this idea can be applied for more complex shapes. So here we have a rectangle with a long side labeled with L and a wide side labeled with W. So the area of this rectangle, A, is calculated by taking the product of those two dimensions, so L times W. A note here, which is very important, is that the units for those two dimensions must be the same. So either both have to be in inches, or both in feet, or both in centimeters, or both in meters. We cannot have mixed units. For example, we can't have L measured in inches and W measured in feet, or L measured in meters and W measured in centimeters. Then calculating the area of this rectangle makes no sense. So both lengths, both dimensions must have the same unit. So as an example, let's calculate the area of a rectangle that has 3 centimeters long side and 2 centimeters wide side. So multiplying the length by the width, we get 3 centimeters times 2 centimeters. And so here I'm going to rearrange the notation. So I'm going to multiply 3 by 2, which will give me the value of the area, the actual number for the area of this rectangle. And then I'm going to multiply the units of each dimension separately. So we have centimeters times centimeters. And so the result of this is that the area is equal to 6. And then the units of the area will be square units now. So centimeters times centimeters. That is centimeters to the second power, or centimeters squared. So here, as you can see, when I multiply the two lengths, the two quantities for the length, I multiply their values, their numerical values separately, and then I multiply their units separately as well. And so this applies for any type of calculation when we have quantities multiplied or divided by each other. So we multiply their actual values or divide their values, however the calculation is, and then their units separately are going to get multiplied or divided, whatever the relationship is. A little bit more of a special case is the calculation of the area of a circle. So here we do not have a long side and a wide side that we multiply by each other. Rather, we can use the radius of a circle or the diameter of a circle to calculate the area. So consider a circle with radius r. The area of the circle is calculated as the product of pi and the square of the radius r squared. So if the radius is measured in centimeters, as you can see, I'm multiplying the radius by itself once. So that means that here I'm going to get, from here I'm going to get the square unit for the area, square centimeters in this case. If the radius was in inches, then the area would be square inches, and so on and so forth. Now, if I know the diameter instead of the radius, the diameter d, then the area of the circle is calculated as pi times d to the second power divided by 4. And so the relationship between the radius and the diameter is that the diameter of a circle is equal to 2 times the radius of a circle. Now, if we had a complex shape and we wanted to find the area of that shape, a good method for that would be to divide the shape into easier to calculate the areas of shapes and then add the results together. So here is an example of that. So here is my shape. I still selected it to be fairly nice so that I can show the example easily, but this method will work for any random shape as well. So I have my shape which has nice rectangular features. And so what I can do is I can divide this in 3 shapes, or in 3 parts. How I'm going to divide that really doesn't matter. Let's say I go like so. I divide this shape into 3 rectangles, for which if I know the dimensions of each rectangle, I can calculate the areas. So let's say the area of this rectangle is A1, the area of this rectangle is A2, the area of this rectangle is A3. So then I can calculate the total area A as just the sum of A1 plus A2 plus A3. And so for any kind of shape, similar method can be applied. Another physical quantity which has a unit that's derived from the unit for length is the volume. So the volume of a figure is the number of cubic units that it contains. So here is a nice rectangular shape. To calculate the volume of this shape, I must multiply its 3 dimensions, the length of the 3 dimensions. So the value of the length, the value of the value of the width, and the value of the height, h. So the volume will be the product of L times W times h. And so here, again, it's important that all 3 dimensions have the same units of measure. The length, the width, and the height all have to be in the same units. Inches, centimeters, meters, feet, it doesn't matter. But we cannot have mixed units because then the calculation of the volume makes no sense. And so when I multiply the values of those 3 dimensions, I will again multiply their actual numbers separately, and then I will multiply their units separately, and so that will give me the unit for volume. Common units for volume would be cubic inches, cubic feet, cubic meters, cubic centimeters. So as an example, let's calculate the volume of this shape here with dimensions of 3 centimeters by 3 centimeters, 2 centimeters by 3 centimeters by 5 centimeters. So again, as I said, I'm going to multiply the values of these 3 dimensions, 2 by 3 by 5, and then separately I will multiply their units, so centimeters times centimeters times centimeters. And so the result of the multiplication is 30, and the units for volume here will be cubic centimeters. So again, centimeters times centimeters times centimeters, that is centimeters to the 3rd power, cubic centimeters. So this is how the volume is calculated of any shape. Now we have one more specific shape that we must discuss, and that is the cylinder. So the calculation of the volume of a cylinder is not exactly done the same way as the calculation of the volume of a nice rectangular shape like this one. So here is a cylinder which has a base which is a circle with radius r, and the cylinder also has height h. So then the area of that the volume of that cylinder will be calculated as the product of the area of the base, which we know is pi r squared, and the height of the cylinder h. And so that's how this is calculated. So from the radius to the second power, we are going to get an area unit, and then we multiply this by the unit of the height. And so again, the dimensions have to be in the same unit. So the radius would be in centimeters, inches, feet. And then the height will also be in centimeters, inches, or feet. So both have to be compatible units, the same units. And so then we multiply squared units by the units of the height. Here we are going to get the units to the third power, so volume units. The question now is also, how do we calculate the volume of a complex shape? So I'm going to illustrate the idea by using a fairly symmetric rectangular shape, but not just a single rectangle. And basically what we will have to do is just split that shape into several nice rectangular shapes, calculate the volume of each of those, and then add the volumes together. So here is one such shape. It's fairly symmetric still, so it's easy to split into smaller shapes for which I can calculate the volume easy. So let's say I'm going to do the split like so. So now I have 3 rectangular shapes for which I can calculate the volumes. And so let's say the first one has a volume V1, the second one has a volume V2, the third one has a volume V3. So then the total volume will be just the sum of those, which would be V1 plus V2 plus V3. So this idea can be used for more complex shapes that are still nice and easy to separate into calculatable volumes. Okay, now let's talk about conversions, unit conversions between area units and unit conversions between volume units. First, let's talk about area. So let's consider the conversion from square centimeters to square meters. The same logic will apply for converting between other units of area. So let's look at this square, which has sides of 1 centimeter by 1 centimeter. So the area of this square is simply the product of 1 centimeter times 1 centimeter. And now if I want to convert this area into meters, what I would do is I would convert each dimension separately from centimeters to meters. So I know that 100 centimeters are equal to 1 meter. And since centimeters is my old unit here and here, that means that in my conversion factor, the old unit centimeters must be in the denominator, since in the original quantity the old units are in the numerator, and the new units, the meters, will be in the numerator of the conversion factor. Okay, so then I want to convert 1 centimeter to meters. Let's do that. So I multiply 1 centimeter by 1 meter divided by 100 centimeters. So this would be 1 centimeter times 1 meter divided by 100 centimeters. The units of centimeters cancel out. So what I'm left with for the final result is that 1 centimeter is equal to 1/100 of a meter, or that is 0.01 meters, or that is 10 to the negative 2 times to the minus second power meters. So here I just converted the first quantity in the area calculation. So I also need to convert the second quantity in the area calculation. So the conversion is exactly the same. So for the second quantity, I get the same result. So now I multiply those two, and that is going to give me the area of this square here, but now in meters squared. So 1 centimeter times 1 centimeter is 1 centimeter squared. So I do a conversion, and I apply the conversion factor that I just explained here to each of those two dimensions. So I already know that 1 centimeter is equal to 10 to the negative 2 meters. So multiply 10 to the negative 2 meters by 10 to the negative 2 meters. That is equal to 10 to the negative 4th meters. So 1 square centimeter is equal to 10 to the negative 4 meters. I can also use one of the other two results, such as that 1 centimeter is equal to 1/100 of a meter. So I will multiply 1/100 of a meter by 1/100 of a meter, and that is equal to 1/10,000th of a meter. So, and of course, these would be squared units. So 1 square centimeter is equal to 1/1000th of a square meter. Finally, I can use the last relationship that 1 centimeter is equal to 0.01 meters. So 0.01 meters times 0.01 meters is equal to 0.0001 meters. And of course, all of these are squared. And so these are three equivalent representations of a square centimeter. So one more time, 1 square centimeter is equal to 10 to the negative 4 square meters, or 1/10,000th of a square meter, or 0.0001 square meters. So any of those relationships can be used to create a conversion factor that converts from square centimeters into square meters. So we are going to use that to do an actual example with a number that is with value for the area that is not just 1, just to show how the calculation goes. So let's convert 4 square centimeters into square meters. So we know from the previous slide that 1 square centimeter is equal to 1/10,000th of a square meter. So I can rewrite this as 10,000 square centimeters are equal to 1 square meter. And so I'm going to use this relationship to create my conversion factor. So here, centimeters squared are the old unit, and meters squared are the new unit. Since centimeters squared are in the numerator, that means that in the conversion factors, they have to be in the denominator. So the conversion factor for this conversion will be 1 square meter divided by 10,000 square centimeters. So then 4 centimeters squared times 1 square meter divided by 10,000 square centimeters, that I can rewrite as 4 square centimeters times 1 square meter, the entire thing divided by 10,000 square centimeters. The square centimeter units here and here cancel out, and then I have what's left is 4 divided by 10,000. The new units will be square meters. So when you calculate that, that is equal to 0.004 square meters, or if I wanted to present this in scientific notation, that will be 4 times 10 to the negative 4th square meters. So there are all kinds of conversion factors that can be derived for conversions from between different area units. So I have provided a table with those conversion factors for you guys to use without having to derive them. I just wanted to explain the logic of how the conversion factors are derived so that you understand better how to use them. Now let's do a conversion of volume units. So let's do the following conversion. Now this is for volume. Let's convert 3 cubic meters into cubic millimeters. So I'm not going to go through the derivation of the relationship between cubic millimeters and cubic meters and then the conversion factor. Again, the table that I've provided for you has all the conversion factors written, so you can just take them from there. So here the old unit is cubic meters and the new unit is cubic millimeters. So when I'm looking for the conversion factor from cubic meters to cubic millimeters, I must use a conversion factor that has the cubic meters in the denominator and the cubic millimeters in the numerator. So from the table with conversion factors, I see that the conversion factor that I must use is this one. So that is 1 billion cubic millimeters divided by 1 cubic meter. So 3 cubic meters times 1 billion cubic millimeters divided by 1 cubic meter is equal to 3 cubic meters times 1 billion cubic millimeters, the whole thing divided by 1 cubic meter. I can cancel the cubic meter units here and here. And so what I'm left with is 3 billion cubic millimeters. And I can also write this in scientific notation. So that would be 3 times 10 to the 9th cubic millimeters in scientific notation. So again, there's all kinds of conversion factors for area, volume, and lengths units in the table that is available for you guys to use. So you can get them from there. And so this basically concludes the lecture on Chapter 1, the Physics Toolkit.